Dubai does not defeat heat, it moves it. Inside a chilled apartment or a glowing hotel, the air feels perfectly engineered. But cooling a city creates an invisible river of displaced energy. Through a thermal camera, the skyline reveals condenser fans pushing massive volumes of hot air back outside. Look toward the coast, and you find immense intake pipes drawing from the sea. The system cooling this skyline is deeply connected to the system producing this cold glass of drinking water. How can cooling a city make the environment supporting that city harder to manage? To understand the scale of this thermal river, we must temporarily ignore the skyline and follow one single unit of heat. It begins when sunlight strikes a glass window. The indoor air becomes uncomfortable. A cooling system steps in to remove that heat. It transfers the thermal energy to a refrigerant. A compressor then forces that energy uphill. The heat passes into a condenser or a district cooling plant. This process consumes electricity. That electrical demand travels through the grid. It ends at a massive power facility. The power facility generates additional thermal losses while keeping the machinery alive. At the exact same time, Dubai draws seawater to run its desalination processes. Fresh water leaves the process. A concentrated discharge remains behind. Some of this combined heat and residual brine returns toward the coastal environment. And the city must repeat this exact process continuously as demand grows. Where does the heat go? What powers the machines moving it? What happens when thousands of buildings do this simultaneously? Why does the answer eventually lead to seawater? The heat never disappeared. It only changed address. In Dubai, cooling and drinking water are not separate problems. They are two sides of the same machine. An air conditioner does not manufacture cold. It uses mechanical work to move heat against its natural direction. The energy rejected outside is always greater than the heat removed from the interior. It includes the warmth pulled from the room, plus the thermal energy added by the compressor and supporting machinery. Inside an apartment, a refrigerant steals heat from the air. A compressor then forces that heat uphill until it can be released outside. Multiply that physical process by one residential tower. The mechanical floors hum with chillers and pumps. They displace the collective thermal load of the building into the surrounding atmosphere. Expand the scale to a district. District cooling plants aggregate the demand. They run massive chillers to push cold water into thousands of homes. Now expand the scale to the entire city. The machinery keeping the desert outside requires a continuous thermodynamic exhaust. Step out of a perfectly chilled lobby into the intense outdoor heat, and the reality of this machine becomes physically obvious. The room feels colder. The street does not. The local atmosphere absorbs this immense urban heat rejection. It creates localized microclimates around dense infrastructure. But the cycle does not end at the condenser fan. Every pump, chiller, and compressor moving this heat requires electricity. This electrical demand creates another layer of mechanical work and thermal losses that the building occupant never sees. Connecting the building to the electricity system reveals the true cost of thermal comfort. Chillers need immense amounts of electricity to run their compressors. Pumps require continuous power to circulate chilled water through extensive urban cooling networks. District cooling can significantly improve system efficiency, but it still relies on a massive, uninterrupted supply of baseline energy. The environment is hardest to reject heat into when the cooling system is being asked to move the most heat. The hottest hour of a summer afternoon is also the hour when the city asks its machinery to run at maximum capacity. In 2025, the annual peak electricity demand of Dubai reached approximately 11.39 gigawatts. That figure represents steady year-over-year growth. It is driven heavily by the sheer volume of air conditioning required to maintain the interior world. So where does the second layer of heat go? The turbines generating that 11.39 gigawatts produce their own immense thermal byproducts. Power lines transport electricity inward. Power generation facilities require their own massive cooling systems outward. Follow the heavy infrastructure to the coast, and you find the turbines, the pumps, and the industrial cooling networks. Large coastal power plants often rely on seawater to condense the steam used in power generation. They pull in cooler ocean water and return it significantly warmer. An underwater thermal plume forms where this industrial machinery meets the ocean. It mixes displaced energy back into the local marine ecosystem. The heat never disappeared. It only changed address. But beside the machines producing this electricity sits another system that Dubai absolutely cannot live without. It is the desalination network. The Gulf is not an infinite open ocean heat sink. From the beach, the water appears endless, blue, and deep. Thermodynamically, it behaves more like a shallow room connected to the ocean through a narrow doorway. Scientific literature describes this body of water as naturally shallow and semi-enclosed. It is subject to exceptionally high summer sea surface temperatures. It is naturally saline, driven by intense regional evaporation and virtually non-existent rainfall. Its only connection to the vast, diluting volume of the Arabian Sea is the narrow Strait of Hormuz. Its internal circulation is heavily influenced by wind, extreme humidity, and distinct seasonal temperature shifts. When massive industrial infrastructure relies on the Gulf for cooling, the central problem is not merely that the resulting discharge might be warm. The problem is that the receiving water already begins the thermal process under extreme environmental conditions. The background temperature against which every new discharge must dilute is rising. Parts of the regional power and industrial cooling systems return their residual heat toward these coastal waters. The ocean must absorb this energy. It relies on tides and currents to mix the thermal plume into the broader basin. But a shallow, semi-enclosed sea has physical limits on how quickly it can distribute sudden, localized energy. The machinery operating on the coastline is effectively adding continuous thermal pressure to a marine ecosystem. That ecosystem is already operating near its natural biological thresholds. This is where the cycle of urban comfort meets the reality of geography. The city pulls electricity from coastal plants to power the chillers that cool the towers. The power plants pull seawater to cool their turbines, returning heat to a constrained marine basin. Then Dubai removes fresh water from that exact same sea, and it returns what remains. The existence of the city requires an astonishing volume of drinking water. By 2025, the desalinated water demand of Dubai reached approximately 161.5 billion imperial gallons. To meet this, installed desalination capacity expanded to approximately 555 million imperial gallons per day by early 2026. This water is manufactured through two primary methods. Older thermal desalination facilities use intense heat and phase change, boiling seawater to capture the pure vapor. Modern reverse osmosis facilities use immense mechanical pressure to push seawater through microscopic membranes. Both methods successfully produce life-sustaining fresh water, and both methods leave a highly concentrated stream of residual liquid behind. Modern reverse osmosis generally uses significantly less energy than older thermal desalination systems. This marks a major technological shift, but the fundamental physics of separating salt from water remain unchanged. Seawater enters one side of the massive coastal infrastructure at places like Jebel Ali or Hassian. Fresh water leaves through one pipe. The rejected salt, residual heat, and treatment stream leave through another. This concentrated brine is discharged back into the Gulf. It adds localized salinity to the immediate coastal environment. The infrastructure is a marvel of human engineering, keeping a desert metropolis hydrated year-round. But it forces a deeply uncomfortable retention question. What happens when the source water becomes warmer, saltier, more turbid, or biologically harder to process? If the Gulf absorbs more heat and concentrated brine over decades, the intake water fundamentally changes. The machines would have to work harder to extract the same amount of pure water. Fortunately, Dubai already has a response to this growing pressure. The solution is more efficient technology. The engineering strategies deployed across the city are real and highly valuable. Dubai aims for district cooling to reach approximately 40% market penetration by 2030. This will drastically reduce the electricity needed to chill individual buildings. The massive Hassian Seawater reverse osmosis project is designed to produce 180 million imperial gallons per day by 2027. It utilizes highly efficient membrane technology. The Electricity and Water Authority is actively pursuing a strategy that involves cleaner energy generation. They are integrating waste heat recovery and improved system monitoring. Engineers are designing better diffusers to rapidly mix concentrated brine into the coastal currents. This minimizes localized environmental concentration. The city is heavily expanding its use of recycled water for district cooling operations. This preserves valuable potable water for human consumption. More efficient pumps, smarter chillers, and advanced monitoring systems are constantly being integrated into the grid. Looking at these upgrades, it is easy to believe the system may already be solving the problem. But efficiency changes the equation, not the law of thermodynamics. Efficiency reduces the energy or water used per unit of service. It means cooling one apartment requires slightly less electricity. It means producing 1 gallon of water requires slightly less pressure. It does not guarantee that total electricity demand, total water demand, or total heat rejection will decline. Not if the overall demand of the city grows faster than the efficiency gains. Efficiency can slow the growth of thermal debt. It does not erase the debt. This is why annual peak electricity demand and desalinated water demand continue to break historical records. A highly efficient air conditioner still rejects heat into the atmosphere. A highly efficient reverse osmosis plant still discharges concentrated brine into the Gulf. Lower impact per unit cannot mathematically reverse the environmental burden if the total number of units continues to multiply. The machine can become more efficient while the burden surrounding it still becomes larger. When total demand outpaces efficiency, the city enters a closed network of compounding pressures. Hotter ambient air requires greater cooling demand inside the glass towers. Greater cooling demand triggers higher electricity demand across the grid. Higher electricity demand forces coastal power plants to reject more heat into the atmosphere and the sea. Simultaneously, a growing population drives an ever-increasing water demand. Increased water demand requires higher desalination throughput at the coastal facilities. Higher throughput leaves behind a massive volume of concentrated residual discharge. That discharge creates additional local pressure around the coastal outfalls. And those altered coastal conditions create more demanding summer operating conditions for the exact machinery keeping the city alive. The feedback is not one dramatic event. It is a collection of small pressures reinforcing one another. The loop is almost silent. You hear compressors, pumps, and water moving through immense concrete chambers. But you never hear the moment when the safety margin becomes smaller. Scientific models must balance these local pressures against broader climatic forces. Basin-wide salinity averages may show much smaller changes than the localized measurements taken directly near particular industrial outlets. Climate change, natural evaporation, and overall ocean circulation remain the major drivers of baseline conditions in the Gulf. However, the localized and long-term impacts of continuous industrial discharge still require intense, ongoing monitoring. Research indicates that the effects of desalination discharge can be substantially stronger near plants and outfalls than when measured as a basin-wide average. This is not proof that desalination is about to destabilize the entire Gulf. It is evidence that local and long-term risks cannot be reduced to one basin-wide average. The stress concentrates exactly where the massive infrastructure relies on the environment the most. If the water near an intake pipe becomes too warm or too biologically active, the average temperature 50 miles offshore does not matter. Infrastructure rarely fails at its average point. It fails at its weakest point. The first weak link lies beneath the surface of the sea, where the machine meets the biology. Seawater intakes are highly sensitive engineering bottlenecks. They face continuous physical and biological pressures. These include sudden algae blooms, jellyfish swarms, suspended sediment, and sudden spikes in turbidity. Biofouling inside the massive concrete pipes can restrict water flow. Combined with extreme seasonal temperature changes, this can force facility operators to constantly adjust their filtering processes. Changing source water quality is an ongoing hazard to manage. It requires relentless monitoring and maintenance to prevent flow restrictions. The second weak link is peak electricity demand during the harshest months. Extreme heat can unpredictably increase the sudden cooling load on the grid. A severe, prolonged heat wave reduces maintenance flexibility. It gives engineers fewer safe windows to take turbines offline for repair. It creates a high-stakes scenario where an ordinary mechanical failure occurs at the worst possible hour. This compresses the critical safety margin between the power the city actively demands and the generating capacity currently available. The third weak link involves the coastal ecosystems themselves. The Gulf is home to resilient coral reefs, seagrass beds, and benthic organisms. Many of these organisms already live near their extreme thermal tolerances. The ecological importance of local conditions near discharge zones cannot be ignored. These marine habitats provide natural resilience to the broader coastline. When these three links are placed under simultaneous pressure, the vulnerability transfers directly back to the human spaces. Think about a busy urban hospital, a luxury waterfront hotel, a dense residential tower, a crowded lift lobby, a simple kitchen tap. How long would a modern desert city remain comfortable if cooling became intermittently unreliable? And how long would it remain functional if water production became harder at the exact same time? Infrastructure does not need to collapse to become vulnerable. It only needs to lose enough margin that an ordinary disruption arrives on an extraordinary day. At this point, a vital counterargument must be firmly acknowledged. The Gulf contains an enormous, naturally dynamic volume of water. Tides, surface wind, and natural ocean circulation provide continuous, large-scale mixing across the basin. Vital water exchange occurs constantly through the Strait of Hormuz. This links the enclosed sea to the broader ocean. Global climate shifts and natural surface evaporation can heavily dominate any basin-wide salinity or temperature changes. These global factors often outweigh the localized impact of human infrastructure on a macro scale. Furthermore, modern discharge diffusers and carefully mapped outlet locations are specifically engineered to maximize rapid, safe dilution. Dubai is heavily investing in more efficient reverse osmosis water production and advanced district cooling technology. The local authorities explicitly state that they rigorously monitor the physical, chemical, and microbiological characteristics of both seawater intake and brine discharge samples. The evidence does not support the simple claim that Dubai is single-handedly heating the entire Gulf. That is an unsupported narrative. A growing city is adding local industrial heat and concentrated discharge to a marine system whose background temperature is already extreme and changing. The uncomfortable part is not that any single machine appears reckless. It is that every machine can be rational on its own, while the combined system continues to grow exponentially. We must clearly separate the fiction from the physical reality. The unsupported claim is that Dubai is causing all regional Gulf warming. The defensible investigation is that massive infrastructure adds undeniable, cumulative pressure at the specific physical points where the city and the sea meet. The question is not whether Dubai is boiling the Gulf. The question is how much safety margin remains at the places where the city and the sea physically meet. Replacing vague doom with measurable physical tests reveals whether the system is actually adapting. There are 4 clear indicators that will determine long-term resilience. Indicator 1 is the strict monitoring of temperature and salinity near specific outfalls, not only relying on Gulf-wide averages. Indicator 2 is tracking the energy used per unit of cooling and freshwater, together with the total system demand. Indicator 3 is the aggressive expansion and use of recycled water in district cooling operations. Indicator 4 is the demonstrable resilience of seawater intakes to temperature spikes, algae blooms, turbidity, biofouling, and sudden seasonal changes. The technological solutions exist, but none of them should be treated as a standalone miracle. Reverse osmosis can substantially reduce the energy intensity of desalination. Cleaner electricity from solar sources can reduce the carbon emissions associated with power generation. District cooling can drastically improve overall system efficiency across residential neighborhoods. Recycled water can reduce the unnecessary extraction of potable water for industrial use. Waste heat recovery can capture and reuse thermal energy to improve particular industrial processes. Better underwater diffusers can successfully reduce localized brine concentration. Strategic demand management can flatten the curve and reduce peak stress on the grid during summer afternoons. And continuous environmental monitoring can reveal changing biological conditions before they threaten the intakes. The ultimate test is not whether the city can build more machines. The ultimate test is whether the city can balance its thermodynamics. Dubai's greatest engineering challenge may no longer be creating more cooling. It may be learning how to cool without continuously expanding the burden placed on the environment that absorbs the waste. Return to the perfectly cold room where this investigation began. The silent thermostat holds the indoor temperature perfectly steady against the summer. Chilled water rises seamlessly through the hidden core of the residential tower. A clear glass of drinking water rests quietly on a table. Outside, the heavily illuminated city operates completely normally in the dark. Nothing looks broken. But visible, everyday normality does not mean the underlying infrastructural system possesses an unlimited margin of safety. Every single degree of heat, forcefully removed from a luxury room, must still be released somewhere into the atmosphere. Every immense quantity of pure freshwater extracted from the seawater leaves a heavy, highly concentrated residual stream behind. Every new expansion of the urban footprint dramatically increases the critical importance of understanding exactly where the heat, the salt, and the energy losses actually go. Dubai was constructed around the incredible engineering ability to create a controlled, pristine interior world perfectly separated from the harsh desert outside. But the shallow, warming waters of the Gulf reveal that this technological separation is deeply incomplete. The interior comfort and the exterior environment are forever connected by cables, massive intake pipes, industrial pumps, and the unavoidable laws of thermodynamics. There is no outside. The heat never disappeared. It only changed address. This video is for educational and documentary purposes, analyzing urban cooling and desalination infrastructure mechanisms. All models and simulations are based on available public data, official statistics, and scientific literature. Environmental impacts may vary based on specific operational conditions. This content is for informational purposes only and does not constitute professional engineering advice. No copyright infringement intended. How much safety margin would you accept in the system producing your water? Share your perspective in the comments below, and subscribe to Dubai Viral to continue investigating the invisible systems running the modern world.